Hello everyone, I welcome you all to Startup Academy, India's exclusive coaching for ISS examination. As we all have been discussing the theorems on convergence, and in the previous lecture we did the theorem on the convergence, which was law of large numbers. Now in today's lecture, we'll be dealing with another theorem which is very important on the base of convergence, which is central limit theorem. Central limit theorem, which is also known as CLT in short form. So, central limit theorem is another form of theorem on a series of random variables. Suppose we have a sequence of random variables. Suppose we have a sequence of random variable xn where all n is greater than equal to 1. Okay, so, it is all only greater than, where all n is greater than 1. This is a sequence of random variable that are IID. This portion is very important. Identical, independently and identically distributed is very important in central limit theorem. That all the variables in this sequence should be identical and independent of each other. Then, when they are IID and expectation of xi is less than infinity. That means expectation of xi exists or mean exists. And variance of xi also is less than infinity, which also means that variance of xi should exist. Then this theorem states that every sequence of random variables which follows these condition will always be following will always be tending towards normal distribution, whether the distribution is skewed, whether the distribution is discrete, and any other thing that has been present which does not conclude to being a normal distribution. In this theorem states that every sequence of random variable that satisfies these three conditions will always follow normal or will always converge to normal distribution. Let us say how. Let us say our test statistic is Zn. Let us say we are taking our text statistics as Zn, which is nothing but xn minus mu upon sigma upon root n. This will always follow normal distribution with mean mu and variance sigma square. Okay, or in short we can say that Zn converges in distribution to mu or normal distribution. Here it should be normal distribution mu comma sigma square. Whether the distribution is skewed or is it discrete, then also if these three conditions are satisfied, then this doesn't matter, and hence we can say that central limit theorem states that all these z's will always converge to normal distribution. Now there are some tests on this central limit theorem is concluded on the test of mean or the average of this sum or the average. So we can say that the sum, suppose the sum is denoted by Sn, and here we are denoting the average. Average is denoted by, let's suppose, xn bar. So if we are talking about sum or mean average, sum, we all know that sum is equals to sum of all the random variables x1, x2 up till xn. Okay, of the sequence. Now we can say that this sum minus mu upon sigma by root n will always converge into in distribution to normal 0 1. This is one of the results of this theorem. Oh, now if we take average, average is x bar n is equals to 1 upon n into sum, which also can be written as 1 upon n into sum of all the random variables, like this, right? Now here we can also state that this average minus mu upon sigma by root n in distribution will converge to normal with parameters mu and sigma square by n, because when we take the average will always converge to always have the variance sigma square by root n. So these two are one of the most important results of this theorem, which is central limit theorem. Now, as we walk forward, this is known as standardization of mean and variance. In here, we all can see that mean expectation of Sn also exists, which is less than infinity, and variance of Sn exists, which is sigma square, which is less than infinity. And here you can see it is 0, and here you can see it is 1. So it satisfies our all problem, it satisfies our all conditions, and it is also identically and independently distributed. That's why we have got mu and sigma square as its as the mean and variance. And here also mean of x bar n is nothing but mu, which is less than infinity, and variance of x bar n, or the average of all the sequence random variables in the sequence, is sigma square upon n, which is also less than infinity. So both of them exist and they are IID, independently and identically distributed. That's why they satisfy this central limit theorem. These are the important points that should be considered while denoting anything that is following central limit theorem. Now, if we move forward, let us move for, I have told you about sum, I have told you about sample mean. Now let us take two examples. So suppose first of all we are taking that x follows binomial distribution with parameters n and p. Now from here we can say that x is a sequence, so expectation of x will be equal to np, and variance of x will be equal to np 1 minus p, and 1 minus p can also be written as npq, right? Now since this distribution is identically distributed, suppose it has been given in the question that it is IID, independent and identically distributed, all the xi's follows binomial distribution. So this is the question. Now we have to apply central limit theorem on this question. How will we apply that? X bar or xn, simply xn minus mu upon sigma by root n. Now here will will converge in distribution to normal mu sigma square, right? Now from here we can say that expectation of xi is nothing but the mean, which can be taken as mu, and variance of xi is nothing but the variance, which can be taken as sigma square. Now just putting these values in this theorem, we'll be getting our answer, which will be mu is np and sigma square is npq. So here npq, because it was sigma here and not sigma square, so it will be under root npq, and under root n and under root n gets cancelled from the numerator and the denominator. So we'll be getting under root n under root pq. And here we can say that it follows normal distribution, it converges to normal distribution with mu. Mu is np and variance is npq. So this is this is how we denote in binomial distribution. This is how the binomial distribution converges to normal distribution in distribution or in law, anything you can say. Now, if we have another variable xi, suppose let us say yi this time. Yi follow IID random variables follows Bernoulli distribution with parameter p. Suppose this time we have been given this. Now here we know that the expectation of yi's will be np. Sorry, expectation of yi will be p, and variance of yi will be p raised to the power x 1 minus p raised to the power 1 minus x. Right? This is our variance. So here we have to again show how the central limit theorem follows. If we say that x bar, or here it is yn minus mu, mu is p upon variance, which is p 1 minus p raised to the power 1 minus x upon under root n, will converge in distribution function, will always converge to normal distribution with mean p and variance p into 1 minus p raised to the power 1 minus x. These are the variance and mean of this distribution. Okay, and now it will be p raised to the power x. And now if we have to denote for y bar n, which is the average or the mean of these random variables, then it will follow in distribution function. It will follow normal distribution with 0 and 1. Average will always converge to normal distribution having mean 0 and variance 1, as we did in the previous slide. Average always follows this. Okay, now let us move to some of the basic questions of this theorem. And the first statement says that the central limit theorem applies to. So the central limit theorem can apply to only normal population, only symmetric distribution, only continuous distribution. As I told you that whether the distribution is skewed or it is discrete or it is continuous or any other thing that has been provided to us, when three conditions or four, let us say four conditions are satisfied. First is independence of random variables. Second is identicality, whether all the random variables are identical. Third one is that it should be having mean is less than infinite, which is mean is finite. And fourth is variance is less than infinite, which also means that variance is finite. When these four conditions are satisfied, any sequence of random variable can follow central limit theorem, or can be or central limit theorem can be applied to any of the sequence of random variables. These four conditions should be satisfied. So it is not normal, it is not symmetric, it is not continuous, it is any distribution. Option number B, which is any distribution with finite mean and variances. Okay. So now moving forward to another question. All of these are conceptual questions, so as to make you understand this. Now the second question is, according to central limit theorem, the limiting distribution of standardized sample mean is, so as I have told you, when we calculate for sample mean, if we have to make it standard, it is x bar minus mu upon sigma by root n will always converge in distribution to normal distribution with mean 0 and variance 1. Okay, so it is our normal distribution, which is our option number C is correct. Now moving to another question. Here they have given us that x bar n, as I've told you in the previous one, x bar n minus mu upon sigma by root n will converge in distribution to normal distribution with mean 0 and variance 1. So here our option number C is the correct option, right? Direct central limit theorem has been applied here. Now next question. CLT requires. What does CLT requires? The first one is independence of random variables. The second one is identicality. Identically distributed. The third one is finite mean, which is mean of x is less than infinity, which is finite. And the fourth one is variance of x is less than infinity, which is also finite variance. These four conditions are satisfied. Only finite mean? No. Only finite variance? No. Both finite mean and variance? Yes. It is correct option. Option number C is the correct option. Now moving forward to another question. Here they have said the variance of sample mean under CLT is. Now if we are calculating for sample mean, which is this x bar n minus mu upon sigma by root n, it always converges in distribution to normal distribution with mean mu and variance sigma square by n. How does this sample mean arise? So x bar n we are talking about, this is nothing but 1 upon n x1 plus x2 up till xn. Now if we have to calculate the expectation of the sample mean, this will come out to be 1 upon n into expectation of x1 plus expectation of x2 and up till expectation of xn. Now we all know that all these random variables are identical and independently distributed, and all the random variables follow normal distribution, suppose mu and sigma square, right? This has been given. So if they are identical, then all of the means of all the xi's will be mu, and if they are independently distributed, then the cross multiplication or the multiplication will be the different multiplication. So it will be 1 upon n and it will be mu plus mu up till mu. So these are total number of 1, 2 up till n. So n mu's, n mu upon mu will give us mu. That's where this came, this one. So x bar follows normal distribution with mean mu, and if we have to calculate the variance of x bar n. So variance of x bar n is nothing but 1 upon variance of summation xi upon n, right? X bar n can be written like this. Now variance of 1 upon n when comes outside, it will be 1 upon n square, variance of summation xi. Now variance can be taken inside, so it will be 1 upon n square, summation I goes from 1 to n, variance of xi. Now variance of 1 is sigma square, so it will be 1 upon n square, summation I goes from 1 to n, sigma square. But since here no digit of I contains, so it will be 1 upon n square, n into sigma square. So this n and n get cancelled, and we'll be getting sigma square upon n as the variance of x bar n, from where this arrived. So hence the variance of sample mean under central limit theorem is sigma square by n, which is our option number B. Okay, if they would have asked us about the standard error is nothing but equal to under root of variance, which is sigma upon root n. Standard error is this. Now moving towards the last question. The CLT is mainly used for, so CLT has many purpose of usages such as estimation, hypothesis testing, approximation. All of these uses CLT or the standardized form of CLT, so as to compare every sequence or series or every other distribution with the normal distribution. Since normal distribution is the standard distribution in our statistics, so that's why it is used for comparison. And CLT, standardization of CLT plays the major role. So in estimation it is also used, hypothesis testing it is also used, and in approximation it is also used. So our option number D is the correct one, which is all of the above. So that's it for today's lecture. I hope that you understood central limit theorem. These were the very basic questions. We'll be doing more questions on this, numerical based questions, in the next lecture. And till then, you keep on doing or revising your topics, and keep on watching the lecture videos. If you have any doubt, you can ask us in the comment section or on our WhatsApp channel. Only relevant doubts will be answered. All the best. Thank you.
Startup Academy presents Lakshya 2027, an exclusive batch designed only for serious ISS aspirants.